Hi there and welcome to the explanation of the deep learning assignment. I'm going to walk through the notebook that we're going to use for this deep learning assignment, explain a little bit about how to work with those notebooks, and show you how the code works in order to create some of the deep learning networks that we're going to be looking at in this class. So I'm going to start off at the instructions, and within the instructions you'll see a couple of links to the YouTube videos. You will see that there's an explanation on how to sign in and work with Google Colab, which is what we're going to use for our networks. And I'm going to demonstrate this about how to change the runtime type. But as you get further down, you will find that there is a link to our first notebook, which is the MNIST notebook. And this is the one that has an example in it. So I'm going to go ahead and open that up in a new tab here. The first thing that you're going to want to do is save a copy of this in your own drive. So go to File, Save Copy in Drive, and then what it'll do is it'll open a new window with exactly the same notebook, but now saved with your drive and with a slightly different name. So I'm going to close this old one. We'll give this a new name. And then that is saved. Now this is our notebook and we can edit it, change it, adjust it, however we want to do that. To get the notebook to connect, it's going to connect to a runtime in the cloud. So it's going to connect to Google servers, and Google servers are where we're going to run all of our code. You click this button up here in the top right, and then it will pop up with this RAM and disk monitoring one of those little graphs and a little check mark telling you that it is connected. Now it's ready to go. The other thing that we might want to check are a couple of other useful functions before we get into the code itself. If you click on runtime and then change runtime type, this is where you can change either the Python version. You don't want to change the Python version because that will break the code. But you can change whether you use a GPU or a TPU. TPUs are a special type of processor that is optimized to work with neural networks. Now, we've tested with both and we found it's a bit quicker to run on the GPU. But if you wanted to run it on the TPU, you could do that as well. So that's one. The second one that might be helpful to you is under the edit menu here, you can do something called clear all outputs. You'll find that as we run these cells, the output prints out below the cell. And sometimes we want to get rid of that and start all over again from scratch. So we can clear all the output in the edit menu. So clear all outputs. And then under runtime, you can reset all runtimes, and that will, or restart the runtimes as well. And that will basically clear everything out of memory and allow you to start completely fresh from the beginning with a new workbook. Right, so onto the notebook itself. The notebook is a mixture of text and Python code. And you'll see that it typically alternates, although there are some cells where it's together. And the way to move down through the notebook is to click on a cell and then hit Shift and Enter. It will run that cell. If it's text, it will just print the text. Or if it's Python code, it will execute the Python code. And that way, that's how you're going to move down the notebook. And you want to make sure that you run every single cell of Python code. Otherwise, when you get towards the bottom, potentially things will not work because we haven't run a piece of code that it depends on. Now, the way Python works, and I know that you guys have worked a little bit with it in a previous class, is sort of a modular way. So we're going to import, to start with, some of the things that we'll need while we work with our deep neural network. So we'll import some stuff to work with data, some stuff to do math, a couple of other pieces, and then we'll also import this data set. We're also going to import something called Keras. Keras is the module that we'll use, the package that we'll use to develop our neural network. It's a really easy, really readable package, which is super helpful when it comes to designing a network because you're not going to get lost in dealing with the minutiae of how data is passed from one part of the network to another. You just tell it the type of layers that you want, and then it does all of the difficult work all of the calculations behind the scenes for you. So we'll go ahead and import some pieces from there. We'll talk about exactly what those pieces do a little bit later on. First of all, I want to take you through a little bit about what the data looks like and how that data is translated into what the computer sees. So the first thing to do is to go ahead and read in the data. We imported this MNIST data set earlier on in the process. Now we've gone ahead and downloaded that. And what we can do is we can print out the very first image from this data in order to show you what we're looking at. So this is a number 5. We've printed out essentially the first part of the matrix using a custom function. And you can see that it looks like a 5. You have a bar across the top and then a sort of circle down here. This is a 28 by 28 pixel image. So each of these pixels has a value between 0 and 255, depending on how dark that pixel is. So the darker the pixel, the higher the value. And those values, the values for each of the pixels in the shape of this, so 28 by 28, that's what we're going to feed into our neural network. So what we'll do in here is we will go ahead and print the very first value. So instead of now looking, we looked at the picture up here with the show function, and then we're going to print just the values of that matrix. Now it's going to come out a bit funky looking because there isn't enough space to get all of the lines together. But you can see that where the in the top left up here, this line represents this very first line of pixels. We've got all zeros because it's all white. But as we move down through the image, and you have to imagine this part of the line is actually goes all the way over here on the right hand side. You can see that the darker pixels have much higher values than the lighter pixels. And you can almost see as you look down the matrix here that there is a shape, and it's the same shape as we have in the function that we picked up here. So this information is what we're going to feed to the computer. We're going to feed this to the computer in the same format. So it's going to be a square of 28 values across the top with 28 values down the side. And that's what we're going to use to train the model. Now, we also have to do a little bit of manipulation in order to get our targets into the right format. Now, traditionally, in the past, at least during this class, when we have a target, normally we have a single column, and sometimes there are multiple values within that column that we might be trying to target. So if we had 3 classes, we might have a 1, a 2, and a 3. That's the way the values are set up in this particular data set. But what we need for our neural network is actually something slightly different. We need a table instead of a single column with just the binary outcome. So we need to have a column that says, is this digit a 0? And if it's a 0, we have a 1 in that column. And if it's not a 0, we have a 0. If that number is a 5, then we have a 1 in the column for 5. If it's not a 5, we have a 0. And this function, there's a Keras utilities function that does that for us, just called toCategorical. It's going to convert that column that we have into that matrix. The final thing I want to note is that we're putting together a matrix, or sorry, we're putting into the model this 28 by 28 matrix of pixels, and we have 60,000 examples. So when we look at the shape of our training data, instead of it being each row represents an example, and we have essentially 2 dimensions where we have the number of columns and the number of rows, in this case we have a 3-dimensional matrix. So we have each square, which would be equivalent to the columns in our normal data set, actually has 2 dimensions, so 28 by 28. And then we have 60,000 examples of that. So the 60,000 is roughly equivalent to the number of rows in one of the normal data sets that we work with. But then we have essentially 2 values for the columns. So we have a 28 by 28 matrix. So you have to think of these more in 3 dimensions than maybe we would have thought about in some of our other modeling that we've done. Now, with all that said, we are finally ready to walk into creating the model. So the first thing to do is to define the model type. Now, we imported the sequential model type earlier on in the code. A sequential model in Keras is one simply where values are passed from the input layer to the next layer, to the next layer, and then to the output layer, however many layers are in the middle. So values are always passing through the network in a sequential fashion, hence sequential model type. There are other model types within Keras. We're not going to use those as part of this class. They get a lot more complicated. So we're going to stick with the sequential model. Now, there's a number of different types of layers that you can add. So the first thing, as I said, we want to define our model. So we'll come down here. I'll make sure I run the code as we go along. There we go. So the first thing we'll do is we'll create our sequential model. This warning you can ignore. There will be a few of those. Typically, they're warnings about some function that is going away in the future. You can ignore all of those. The code will still run fine. And typically, if you try and run it a second time, the same code a second time, the warning just disappears. Now we have our model type defined. We've told Keras how we want to pass the values from layer to layer. It's time to start adding some layers to it. The first layer that we need to add is the input layer. And there's a couple of special things that go on with the very first layer that don't have to happen with the other layers. Specifically, in this case, we have to define the input shape. Now, I spent a bit of time earlier on discussing that our input shape was a 28 by 28 matrix, not just a list of columns. And I did that because we have to put that in right here to our very first layer. We have to say that what the input shape, what the shape of our image is, because Keras needs to know that in order to make sure that it properly structures the network and that it's able to read the image in. You will have this information in all of the assignment notebooks, so there's no need necessarily to be able to write this, but I want to make sure you understand what it does and why we have an input shape in our very first layer, but we don't have an input shape in any of the other layers. Now, this first layer that we add is something called a dense layer. A dense layer, and I'm going to skip back to our deep learning presentation here. A dense layer is a layer like this, where we have all of the items essentially stacked up on one another. It's what we have traditionally used, or what we've used in other classes when we've been working with neural networks. Typically just a flat, somewhat flat stack of hidden units. That's what is called a dense layer. The other thing about a dense layer is every input unit is connected to every unit in the hidden layer. There's nothing special going on. This is the sort of base layer type. So our first network, we're going to add several dense layers. The units value indicates the number of units that are in each hidden layer. So that will be these dots. You can change that value if you like. To edit the thing, you just click into the cell. You can delete the value and change it as you would like. And that will change, obviously, what the predictions are from the network as we work through it. So let's go ahead and add this first layer. Then let's go ahead and add a second layer. With both of these layers, we've used an activation function called ReLU, labeled ReLU. This is the rectified linear unit function, again, that we talked about in the previous presentation. That function can be added in one of two ways. So right here, we define the first layer, and then we add the activation function to it afterwards. Right here, we define both the layer size and the activation function in the same piece of code. You can do it either way. It works either way just fine. So we've added our first dense layer. We've added our input layer. We've added a second dense layer. Then we're going to add what's called a flatten layer. Now, our matrix, as I've talked about many times or several times now, is 28 by 28. We want to make sure before we go to our output layer that we've flattened that to be a traditional column-like structure. So you can think of that, taking that 28 by 28 matrix and then just squeezing it down. So instead of having 2 dimensions, now we have 1 dimension. That's an important part, particularly when we get to the convolutional neural networks. You'll see that we need this layer in order to make sure that everything gets into the output correctly. And then finally, we're going to add a dense layer that is our output layer. You'll notice 2 things about this. First one, this has to have 10 hidden units. It has 10 units because there are 10 values, 10 potential values that we're trying to predict. If you had 100 values that you were trying to predict, this would need to be 100, and so on and so forth. So first thing to remember, this layer has to have, the final layer, the output layer, has to have the same number of units as you have values that you're trying to predict. Second thing to note is that in all the other layers, we use this rectified linear unit function as the activation function. In the final layer, we're going to use a softmax function. The softmax function is the same as a logistic regression, probably not mathematically the same, but it functions in the same way. The same as the logistic regression function. So essentially, we're going to output a probability between 0 and 1 that the value in the picture corresponds to that particular value, that particular output value. So for a training example, in our first training example, it was a 5. So hopefully, by the time we've trained the network, if we fed it that same image, we get a high probability that it was a 5, but we'd also get a low probability that it was any other number. So again, just a slightly different activation function because this is an output layer and we want to output the probabilities. So now we've added everything to our network. Again, you can change the number of units in each of these internal layers. You will want to keep the number of units in the output layer the same. We want to go ahead and compile the model. So as I said, we've built our model, we've defined what the layers are. Now we want to compile it, which basically means putting it in a nice box, tying a bow on it, and telling it how we want to optimize it. So what do we want to use to define whether it's moving in the right direction as it trains, and what is the optimization function that we want to use to train it and to adjust the weights within the network as it goes through the training process. In this case, we're going to use something called categorical cross-entropy. That's basically trying to optimize across a number of categories. That is the best loss function to use. And then we're going to use this optimizer called adder delta. You can, if you would like, change the optimizer. There's a bunch of options within Keras. You don't really need to. They all work in a pretty similar way. They're not going to have that much of an impact on the results, but the option is there. And we're also going to have it print out the accuracy for us. The accuracy for us would be between 0 and 1. So 1 will be 100% accurate, 0 will be 0% accurate. We're going to have it print out the accuracy for us as it trains the model. So we'll go ahead and compile it. The next thing we're going to do is train the model. So to do that, we use a model. We write model.fit. We define the data that we want to use to train it. That's the data. We give it the labels. That's the actual value for that particular piece of data. We tell it how many times we want it to pass all the way through the data. And then we tell it how many examples we want it to look at before it updates the weights. So epochs, the number of times it passes through the whole training data. And then the batch size, which is the number of examples it will look at before it goes back and updates the weights. So it's going to go through 128 examples, decide how the weights should be updated based on those 128 examples, update the weights, and then run through the next batch of 128. And it's going to do that all the way through the data set 10 times. So let's go ahead and kick this off. You'll see it prints out some warnings. Again, can mostly ignore the warnings. They'll go away if you run it a second time. On this particular platform, the training runs quite quickly. You'll see that the loss function is going down. That's good. That's exactly what we want, while the accuracy is going up. You can see we're passing through the training data each time. So we're now on 5 of 10, now 6 of 10. And this takes just a couple of minutes. Now, bear in mind, the training will take longer. The more you pass through the data, so if you added 20 epochs, or if you had 20 epochs, that would take longer. It also takes longer based on the complexity of the network itself. So we have quite a simple network in this example. So a simple network is training relatively quickly. If we had a much more complicated network, which we'll get to in a second, that will train quite a bit slower, sometimes a lot slower, depending on what you do. Having said that, typically trains a lot faster on Google's compute power in the cloud than it does downloading it to your own laptop and working with it there. So now that we've finished training, we can look at this final step. We can see that the loss function went down to 0.08 and our accuracy is 0.97. So fairly accurate network. It's a fairly simple data set. But we also want to make sure that we look at the results on the test data. To do that, you can use this handy little cell down here. This is available to you in the other notebooks as well, and that will tell you, it will just test the network against the testing data by passing through this model.evaluate function. Is super helpful because you just pass it the testing data and the test labels, and then it will output what the score is. And it will tell you, as you can see here, what the loss is and what the accuracy is. So in this case, we got 95.68% accurate on our training data versus 97.64% accurate on the testing data, on the training data, which is pretty good. But what if we used a more complicated network type? So we've talked a lot about convolutional neural networks and how they're able to understand the space and the relationships between what goes on in different pixels, as opposed to dense networks where it's really just brute force throwing all the numbers at it and seeing what comes out. So let's go ahead and build ourselves a convolutional neural network. So again, the first thing we're going to do is define the model type. We're also going to import some different types of layers. So a convolutional layer, a max pooling layer, a dropout layer, and a batch normalization layer. And then we're going to add several sets of layers to our network. Convolutional networks, I like to think of them in terms of sets. So this is the first set of layers, the second set of layers, and the third set of layers. You don't have to stick strictly to that pattern. You can experiment with moving different types of layers in different places, putting them in different orders and things like that. But this particular process typically gets you a network that trains fairly easily, and you don't run into too many issues with it. Each set of layers consists of, as you can see, 4 layers. The first one is the convolutional layer. So this is the layer that is essentially scanning across the image and looking at the relationship between the pixels. Note that on the very first layer, and on the very first layer only, we have to define the input shape. So that's the shape of the matrix that we're feeding it that represents our image. Again, you'll have the input shape written in the first layer on all of the example networks, but you'll want to take it out, as you can see, once you get to the second set of layers. You can adjust a couple of things in here. Filters. Filters is roughly analogous to the number of units in the hidden layer. And then the kernel size, which is the size of the scan, essentially. How big of a window are we looking at for relationships between those two, or between the pixels? The second layer that we add is called a max pooling layer. This layer is designed to pull out the most significant features within each of those windows. So if you think of it as a window moving across the image, the max pooling layer looks at that window and then pulls out the most significant feature within that window. Again, you can decide how big you want this to be. Then we have a dropout layer. The dropout layer is a layer designed to prevent overfitting. So what that does is essentially pause the updates on a random portion of the network. So in this case, we're going to pause updating 20% of the neurons each time the network updates as it trains. The reason we do this is because we don't want it converging too quickly and too specifically on too few examples. So we're essentially putting the brakes on how quickly it trains in order to get a model that generalizes much better onto unseen data. And then the final layer we have within this set of layers is something called a batch normalization layer. And what that will do is that will normalize the values across several examples and within the matrix itself to make sure that we don't end up getting values that may be really big or values that may be really small. The way to think of this is whether somebody writes a 5 with a really heavy hand or whether they write it very, very gently, we don't want that to have an impact on whether we're able to identify that as a 5 or not. We just want to know that it's a 5. And the batch normalization layer helps with that. And it helps with how we pick out those significant, or how we pick out the significant features each time to make sure that we're not picking out just something that happens to be a really dark bit because somebody has a particularly heavy hand when they wrote the numbers. Here we'll add a second set of layers, again with the convolutional layer, the max pooling layer, the dropout layer, and a normalization layer, and then a third set of layers with the same layout. As I said, you can adjust the filter size, you can adjust the kernel size, you can adjust the pool size, and you can adjust the amount of dropout, how much we pause the network as it trains. All of those parameters are tunable, so feel free to play around with them to your heart's content. One of the things that you'll notice is that as the data passes through the network, the size and shape of the matrix will change. So this input shape up here starts off as 28 by 28, but each time we pass through a particular set of layers, actually each time we pass through a layer, the size and shape of that changes. So I think this is a great example of that, where we have our big flat image to start with. Then we look at a different shape. You see it sort of squashed it down to be from being very big and thin to being slightly shorter and slightly fatter. And then we've continued to change each of these and essentially pull it long and thin as we work through our network, through each layer of our network. One of the things to note is that as you do that, you want to make sure that the number of filters, the kernel size option, etc., 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 don't end up trying to take away too many dimensions. So in this version, if we try to take away too many dimensions at this stage here, we might end up trying to squash the network down to nothing. This will give you an error. So if you get an error that says something about negative dimensions, what you want to do is go back through the layers. Typically reducing the kernel size or reducing the pool size will help fix that. Finally, we're going to add our flatten layer and then our final dense output layer with the activation function softmax to get our predictions. We're going to do the same thing. We're going to compile it. Nothing has actually changed in the compile step. It's exactly the same as we did for the dense model. And now we're going to go ahead and we're going to fit the model. Now, notice still training for 10 epochs, have the same batch size, but note how much slower this one's going. In the other example, it took about 9 seconds for the first layer to train and then about 4 seconds for each layer after that. We can actually see by scrolling up. So it took about 4 seconds for each training layer to complete after the first layer. And this one, it took us 14 seconds for the first layer. It's taken us 9 seconds for the next layer, 10 seconds for the third for each epoch, rather, not layer. 14 seconds for the first epoch, 9 seconds for the second epoch, 10 seconds for the third epoch. Now, typically this will stay pretty flat. We have 3 different values in there, which is a little bit unusual. But as we work through the training and as the networks get more complicated, this is a much, much more complicated network than our previous one, you'll find that the training time goes up, and you can adjust the epochs and the batch size as you play around with it to make the training go a little bit quicker. Typically, if you adjust the batch size up, then the training will go a bit quicker. But you also want to be aware that there is a trade-off in that if you make the training go quicker by adjusting the batch size up or reducing the epochs, the network will not train as much, and therefore it may not be any more accurate, or it may be less accurate than it could be. So we're in the final epoch now. You can see we stabilized around about 10 seconds per step. It's finished training, and our final accuracy is 97.56%. If we scroll up, that is within a gnat's whisker of the training accuracy at the end of the previous, the accuracy with our previous layer. So let's go ahead and score this. And you can see that our accuracy is 0.98. So we actually got a much better score on the test data with the convolutional network than we did with the dense network, even though the overall accuracy on the training data was very, very similar. So that is how you can create your own network. As I said, you can adjust the filters, the kernel size, the pooling size, the dropout. You can add different types of layers. You can even add more dense layers after you flatten the network if you'd like to do that. And you can adjust the epochs and the batch size as to when you train the network in order to, again, train it maybe more times through the data or fewer times through the data, and talk about what that does to accuracy. So I want to talk about a couple of common errors. A couple of things you can do. The final, this model that we had up here, this is called Model 2. So we can print out a little bit of information about Model 2 by using some of these neat functions. So this will print out model2.layers. That just prints out a list of all the layers in the network. You can print out a specific layer by printing out layers, and then in this case, we're looking at layer 0. So that's going to be that first layer. It's going to tell us a little bit about that layer. And we can use input shape and output shape in order to understand how the shape has changed going through each of the layers. So you can see if we look at layer 0, that's our very first input layer. The input shape is 28 by 28. We defined that. And then the output shape is 27 by 236. So we've gone down by 1 in this, and then up to 236 in this. The reason I show you this is because when you get to the negative dimension, or when you end up with a negative dimension error, sometimes you can use this to step through and understand how the shape is changing, and then adjust your filters and things appropriately. Typically, though, you just make them smaller. Now, we've compiled the network, and remember that our final layer is the output layer, which has 10 neurons in it. If I try and add another layer, I get a big and rather scary looking error, because I tried to add a layer to a network that's already been compiled. In order to fix this, you want to add the layer to a new model. So you want to go back up to where it says model or model 2 equals sequential, run that line of code again, and then build the model up from scratch. And typically you will avoid that particular error. Now this piece of code, what we're going to do is this is actually the same piece of code. You can see that we have the first set of layers, second set of layers, third set of layers. What I'm going to do is I'm going to make this pool size something crazy, like 10, and I'm going to see if I can get it to generate an error because we stepped the network down too quickly. There we go. So what's happened here is it's saying that we've got a negative dimension caused by subtracting 10 from 1 in this particular layer because the input shape, essentially we can't subtract 10 because the input shape is already the wrong size. Essentially, we have the wrong size of input. It would make it go negative. One of the helpful things about this is that it will tell you which layer is causing the issue. But typically the way that you would want to fix it is just to go through your network here. And if we take this pooling back down to a more reasonable level and we rerun the cell, you'll see that this will come up. See, it doesn't generate an error because now we've reduced the number of dimensions that we're pooling by, and we won't end up with negative dimensions. So if you get that big scary error, either look at starting the model from scratch using model equals sequential, or stepping down the pool size slightly differently so that you don't end up creating negative dimensions. With that said, feel free to move on to the 2 other notebooks that we have in our instructions, and then reach out to either myself, the TA, or to the professor with any questions that you have. We're happy to help guide you through this assignment, and best of luck. I look forward to seeing what you can come up with.